And welcome back to Mechanical Systems Design. Today we'll be talking about material selection. And as always, if you haven't yet read the topic reading, you'll want to do that first so that you really understand what we're talking about. And we're going to begin with an exercise that we're calling quick draw. So many times you'll have a candidate material and you'll need to know about its key properties. So what I'd like you to do now is pull up your favorite online database like MatWeb or textbook that has material properties in it, and get ready to find the material properties for specific materials that we'll list. Are you ready? The first one is 7075 T6 aluminum, and we'd like to find the yield strength. So pause the video, take a moment, and go find the yield strength of 7075 T6 aluminum. All right, you got it? Hopefully you found something like 73 KSI. Notice that this is about double the yield strength of 6061 aluminum that you usually find hanging around a machine shop. It's only a little bit more expensive, but it's a lot stronger and it's almost equally machinable. So if you're ever trying to design some fancy new robot part, 7075 T6, that's a great way to go. All right, let's do another one of these. What is the ultimate strength of 440C steel? Pause the video, take a moment, and go find this material property. All right, you got it? Or maybe it wasn't so clear, actually, in your poking around. You could have found answers anywhere between 65 to 280,000 PSI. And that's because the ultimate strength and the yield strength and other strength properties of steel will depend on its treatment, especially its heat treatment. And so we haven't given you enough information to know what that answer is. And so that's something important to keep an eye on when you have to use a material and you're assuming some material properties. You want to make sure that you've got those details of treatment right so that it will behave as you expect. Now, when you were poking around, you probably also had the opportunity to look at the elastic modulus and the density of this material. What were those values? Did they exhibit this big range? Probably you did not see such a big range because those properties are much less sensitive to heat treatment. And in fact, basically all steel has approximately the same density across all chemical compositions. All right, let's do one last one of these. What is the elastic modulus of ABS plastic? Pause the video, take a moment, and go look it up. All right, you got an answer? Well, here again, we might have found a pretty big range, somewhere between 200 to 400,000 PSI. And that's going to depend on the forming method, the plastic in this case. Much like heat treatment of the steel, the way that this plastic is formed will affect the way the molecules are aligned, how much cross-linking has happened, and therefore the strength and stiffness of this material. So something to keep an eye on as you think about the interaction between the material you're using and the manufacturing process that you apply. All right, that's our first exercise. Now, an exercise on analytical material selection. This is the focus of the topic reading. And just to review it quickly, what we'll do is a three-step process. First, we'll analytically determine the desired material factor. And to do that, we will use this back of the envelope analysis approach, much like what we've done to find mass optimal part geometries. And well, for example, we'll do a specific example in the next slide. So we'll use that to find the desired material factor, which could be simply high elastic modulus, but most of the time we find out that we want a particular ratio of different properties like yield strength to the square root of yield strength divided by the density, or other combinations of material properties to different factors. Once we have that material factor, we will use a material chart to find some candidate materials that have good values of those properties and their ratios. And these were we have charts that were popularized by Ashby. Some of those are reproduced in Shigley, some in our topic reading, and you can find versions of them all over the internet these days. And then finally, once we have a set of candidate materials, we'll use other considerations to pick the best material for our application. And in particular, manufacturing, which is really strongly influenced by the geometry of the component we're trying to produce, and cost. Those are often important considerations. And sometimes they can be dominant and pull us away from an optimal material factor, but at least then we'll understand the kind of trade-off we're making, and we won't pick a really bad material factor. Okay, so let's root this in a specific example. Here we have an exercise where I'm asking you to pick the best material factor for this loading scenario. And we have a cylindrical column with a fixed base, a free top. It's under a compressive axial load. And the goal in this application is to minimize the mass of the component. So this is a problem that we're now very familiar with. And the question is, what are the best material properties for this application? We've given you some of the key formula there. And what you want to do is, just like in our mass optimization problems from recent discussions, we want to try to distill this down into an equation where you have mass equals a bunch of stuff, and then isolate that material factor and to figure out what the best combination of material properties would be for this problem. All right, hit pause, take a little while to work on this. It should take you maybe 5-10 minutes to work through it all, and then come back and we'll talk through the answers. Got an answer? Let's look through my algebra together. So there are two potential failure modes, and you might have focused on one or the other or both in this case. The simple one is compression. And let's start there. That's on the right-hand side of this slide. So we're worried about exceeding the yield strength in compression. We would write down this: the stress is the force over area, and we want that to equal the yield strength divided by the factor of safety. And so we can reorganize this equation to say the area, which is the geometric term that we get to choose, should equal the force times the factor of safety divided by the yield strength. We can then plug that into an equation for mass. The mass of the part will be the area times the length, that gives us the volume, times the density, and that gives us the total mass. If we plug in our value for A here, find that the mass of our component is force times factor of safety times length times density divided by yield strength. If we reorganize that, we have the mass is equal to this loading stuff times this fixed geometric constraint for our problem, assuming that the length of the column is not something we get to choose, times this material factor, the ratio of the density to the yield strength. And when people say strong but lightweight, I think intuitively this is the kind of thing that we're thinking about. But usually it doesn't turn out that our material factor is an integer ratio of these two terms. So if we look at the buckling case, we can find a more common kind of situation. Here we're concerned about buckling, so we want to use our formula for the critical force at which buckling is expected to occur. And that critical force, we want it to equal the actual expected force times the factor of safety. And we know that the critical force is pi squared EI over 4. We've substituted in the correct coefficient for a fixed free case times the length of the column squared. And we know that in this case, the area moment of inertia, I, is pi r to the fourth power divided by 4. So we plug that in, we'll get that the force times the factor of safety is pi cubed E r to the fourth 16 squared. And here again, if we assume that length is constrained, we have one geometric choice to make. That's with the radius of a column. We isolate that term, we get that the radius to the fourth power is 16 over pi cubed times the force times the factor of safety times the length squared times 1 over the elastic modulus. Now the mass of our column will again be pi r squared, that's the area, times the length, that gives us volume, times the density, gives us the mass. And if we substitute in, we have a value for r to the fourth. We'll take the square root of all of this stuff and substitute that in for r squared here. And we'll get that the mass is pi times 4 divided by pi to the 3/2 power times the square root of force times factor of safety times 1 over the square root of the elastic modulus times L times L times density, or if we combine terms, we get mass is 4 over the square root of pi times the square root of force times factor of safety times, here's our material factor, density divided by the square root of elastic modulus times length squared. So if we want a minimal mass beam that doesn't buckle, we want a small ratio of density to the square root of elastic modulus. Now, we've got our material factors that we care about. Let's go look at some charts. Now, if we just guessed initially based on this is buckling, it's about stiffness, we want a high elastic modulus, we might look at a chart like this where we just have the elastic modulus on the y-axis. And that would suggest something like a tungsten carbide to us. But we saw in our calculations that actually we care about a ratio of these properties. And this doesn't tell us anything about how much those materials will weigh per unit material. So instead, we look at a chart like this where we have elastic modulus on the y-axis and density on the x-axis. And this is a log-log plot. And therefore, these straight lines in this space are lines of constant ratio of properties raised to certain powers. So this line, everything on this line has exactly the same value of elastic modulus divided by density. And everything on this line has exactly the same ratio of elastic modulus to the 1/3 power divided by density. Now, in this case, if we start with buckling, and then we determine that we want a low ratio of density to elastic modulus to the 1/2 power, or equivalently, we want a high ratio of the square root of elastic modulus to density. So everything on this line has a constant value. As we move this line up and to the right, up and to the left, that value gets bigger and bigger, which is good. If we move it out to the edge of the bubbles here, we'll get several candidate materials that all are equivalently good in terms of their material factor. We could have some of these better rigid polymer foams, some hardwood, the proper grain alignment, composites like carbon fiber, or some technical ceramics. To get from this set of materials down to a material that we really want to use, we'll need more information than was provided for the problem. For example, if this is a case where our geometry and scale are appropriate to a molding process, then perhaps a technical ceramic could be a good choice. If it's something that's really big and cost is not a concern, with a very simple shape, then a composite material might be a good choice, like carbon fiber. If cost is really important and it's kind of fairly big and there's sort of high forces at some little points on it, maybe a wood would be a good choice. Or if the loads are pretty low and cost is important and we have pretty well distributed forces on either end of our column, then maybe a foam would be a good choice. So to make that last step, you need a little more information. All right, now what if the yield strength is the dominant failure mode in our case? So then we would need a different space. So here we have the strength on the y-axis to density on the x-axis. And remember that we found that we wanted a good ratio of yield strength to density. So if we, again, move this line up and to the left in the space, everything on this red line has an equal value of that ratio of strength to density. And we've got a different set of materials that would be a good choice. In the previous slide, we saw that we probably wouldn't want to choose most metals because most of them are about an order of magnitude worse in terms of their material factor in this elastic modulus versus density case. We certainly wouldn't want plastics, again, an order of magnitude worse. In this case, we're going to find that some metals actually are quite competitive, but where, again, ceramics and composites would be good choices. Wood wouldn't be as competitive, and foams wouldn't be as competitive if this turned out to be the dominant feeling. And once we got that set of materials, candidate materials, we would again apply these additional considerations, especially manufacturing, geometry, cost considerations, and that would shrink us down to one or two good choices for our material. Now, I think this is sort of intuitive to people, and people kind of think, oh yeah, carbon fiber, everybody knows it has a good strength to weight ratio. But it really does depend on the loading conditions and the geometries that are involved. And if we picked slightly different loading conditions and geometries, we could come up with a situation where we really wanted a high ratio of strength to the 1/3 power divided by density. And if we move that line up and to the left, we'd see that actually, gosh, our composites and ceramics are not good at all compared to foams, which are like an order of magnitude better. So really need to go through that quick analysis. Whatever your objective is, it might be mess, it could be something else, and find out what the material factor is for your case. All right, that's a lot to digest. Why don't we take a quick break, and then we'll come back for one more exercise. All right, and we're back. The last thing I wanted to do here is talk about some intuitive material selection. So, many times we're faced with the need to make a quick decision about what could be a good candidate material, and then do some calculations to figure out how it stacks up. And so if you're for a very narrow set of conditions, which is designing advanced robots in a laboratory for research or other sort of prototyping activities, there are a few materials that come up over and over again as good choices. And I just wanted, this is something that we do in my group a lot, and I wanted to review this quickly for you. So one is aluminum, and it's usually useful when you have a medium-sized component with some complexity and a medium load. We often use steel materials when we have a small component that has a lot of complexity and experiences high load. Plastics are often good for complex geometries that experience low load, and especially cost is a big consideration. And carbon fiber composites are often useful in cases where we have large, very simple components that experience high loads where mass is critical. And some of our favorite precise materials are 7075T6, which we mentioned earlier, grade aluminum, 302 stainless steel, 174 pH stainless steel, very hard. It's a little tough to machine, but very good strength properties. Close to like heat treated 440C almost. Carbon fiber, good for high strength and stiffness applications. Fiberglass with an S class makes great leaf springs. So if you want it to be a little more compliant, fiberglass is a good choice. Teak has good low friction properties and makes a pretty good component plane bearing if you're making some custom component with that built in. ABS is great if you're thermoforming your components, like taking a sheet, warming it up, and putting it over a mold, like a vacuum mold. PLA and acrylic are fantastic if you need to very quickly make something on a 3D printer or laser cutter, and particle work can be great too, although we almost entirely use that for low-fi prototypes. So let's look at a few part designs and make a quick guess as to what materials would be good choices for that component. And here is our first part. So take a look at this engineering drawing. This is a wrist in a robot arm assembly, and try to guess what would be a good material for this part. Pause the video, take a few minutes, think about it, reflect on it, and make a concrete guess. Okay, you have some guesses? There are a few good answers in this case. One would be aluminum, because this is kind of a medium component. We sort of imply these medium loads. There's this place where we're going to put a motor in there, but it's sort of connecting everything together. It's at the end of your robot arm. Maybe you don't want it to be too heavy, and it has a lot lower density than steel. That could be a good choice. Now, an alternate choice would be, say, look, this has threaded holes, a bunch of them, and those threads experience very high stress inside. And if you don't want those threaded holes to wear out really quickly, then steel would be a better choice. And that's a good argument as well. All right, here's another component. Take a look. This is a motor shaft coupler. That's a component that connects the output of the motor to the next element in the transmission. Think about what kind of loads it'll experience, scale, what kind of material would make sense for this part. Make a good guess, pause, make a good guess, and then come back. All right, you got a guess? Yeah, probably we would manufacture this out of a steel because the component is pretty small. It has these complex features like threaded holes, and it experiences pretty high load. I mean, this is going to experience the full torque of the motor, and it's at a critical point in the transmission. So that high density of the steel doesn't hurt us too much, but the high strength of the steel is a real asset. And we might make this out of 302 stainless steel or something. All right, how about this component? Take a look, think about it, make a guess, and then come back. And you can hit pause now. If you got a guess, this would probably be a good choice for plastic. Likely, since it's a spacer, it probably won't experience a lot of loading. It's just there to keep things well aligned, especially when you're putting the system together. So, some kind of plastic, maybe a PEEK. You could probably potentially order a component that has the right size as well. And finally, one more component to make an intuitive guess about a good material for this part. So this is the arm of the robot. Take a look, think about it for a moment, and then make a guess, and then come back. You can hit pause now. But you got to guess. So this is pretty big, a couple of feet long. It's very simple geometry, a plain tube, and it just has a couple of features in it, two holes that are drilled into either end. And this geometry is chosen to be simple like that on purpose because the intention to use carbon fiber, where we can purchase the stock that has the right size, cut it to length, put a few very simple hole features in it, which is still kind of a pain. And then you get a nice stiff, lightweight, large, simple component. All right, so that's a quick overview of material selection. There is a whole diverse, incredible, deep world of material selection and understanding all the complexities of different materials and how they interact, especially with processes like manufacturing. And that is something that you can explore in other courses at Stanford, like the magic of materials in manufacturing, and in some of the other courses on, say, elasticity and inelasticity and things like that. But I hope this gets you a good enough start for your projects in our course.